My name is Marco Durante. I am the director of the biophysics department at the GSI Helmholtz Center in Darmstadt, and I'm also professor of physics at the University of Darmstadt. I worked all my life on biological effects of the heavy ions, essentially charged particle. And I worked first in Berkeley, then at NASA, then in Japan, and then finally I ended up in Germany at GSI. That was the first center in Europe to introduce carbon ion therapy, which is now performed in 4 different centers in Europe, 2 in Germany, 1 in Austria, and 1 in Italy. I was always interested in radiation effects for a strange reason. When I was young, I was very young. I was reading a lot the Marvel comics. That's something I think the new generation doesn't even remember because now they know the movies. But in my age, I'm talking about the 70s, so many, many years ago, we only had these comics, we were reading them. And all the Marvel superheroes, they were all exposed to radiation. It was something really fantastic. You take Spider-Man, he was bitten by a radioactive spider. You take the Fantastic Four, they were exposed in space to a solar particle event. At least now I say it's a solar particle event. In the comics was just strange radiation, You take the Incredible Hulk, he was exposed to gamma rays. And so on and so forth. There were so many superheroes that were exposed to radiation that I became more and more interested in radiation effects as I was a kid. Now, after so many years working with radiation, I can tell you, don't do it at home. It doesn't work. You don't become a superhero. It's always bad. But, it was a good motivation to start. I think it certainly is. We have to be careful, though. We still need a lot of preclinical research because the more research we do, the more we realize that it's a complicated effect, depends on many parameters, and we still don't understand the mechanism. So before clinical translation, we researchers, I'm a researcher, I'm not a clinician, we researchers, we have to do our homework and we have to come out with a plausible mechanism and a clear definition of what are the parameters that make FLASH optimal in clinical environment. At GSI here in Germany, we are specialized in heavy ion radiobiology. So of course, we always worked on the effects of heavy ions. Carbon, but also heavier ions. Also for space research, we use up to iron, for example, iron ions that are very heavy and not used in therapy. Then, of course, when the FLASH started, we decided to focus on our main expertise, which is heavy ion. So we said, first of all, can we do heavy ion FLASH, what we call high FLASH? This was not easy because, of course, to reach these high intensities with synchrotrons is not as easy as with Linux or with the cyclotrons. But eventually we managed it. Both in Heidelberg, in a strong collaboration with the HIT, we were able to reach the FLASH intensities. And of course, at GSI, where it is also easier because we have a higher intensity. So from the physics point of view, it's possible. There was a lot of work on dosimetry, of course. And then we said, okay, next step, we have to do the experiments in animals. So now we are working together with DKFZ in Heidelberg on doing the experiments in mice. We have 3 different protocols, actually, and we are trying to understand whether heavy ion FLASH works. This is important for 3 reasons. The first one is that, of course, if it works, that will be clinically useful because we can use it in the clinics. The clinics that use heavy ions, there are 12 now worldwide in operation. They can go to high intensity and widen this therapeutic window. The second one is going back to the origin of heavy ions. Originally, this story started in Berkeley with Cornelius Tobias. He really wanted to use very heavy ions like argon, or neon, because he really wanted to smash hypoxic tumors. And to do that, you need very high LET. This was not possible because these ions are toxic already in the entrance channel. So eventually, the carbon was used as a compromise between high toxicity and high efficiency. But of course, if FLASH makes the ions less toxic, then it's very likely that we can use heavier ions for therapy. And finally, the third reason is the basic mechanism. At the moment, we don't know the mechanism, but we have many hypotheses related, to the oxygen depletion, to the free radical recombination, to intertract effects, to immune system effects. All these effects are LET dependent. And at the moment, we have FLASH with protons, with electrons, with X-rays, all low LET particles. So when we move to high LET, we will see what is the difference and whether, because all these mechanisms are LET dependent, we will see what the model will predict when we move to high LET, and so we will understand much more about the basic mechanisms of FLASH. FRPT will be an interdisciplinary meeting, bringing together scientists with different backgrounds. We have biologists, chemists, engineers, physicists, of course, and medical doctors. To work into an interdisciplinary field is always difficult because people speak slightly different languages, but it's extremely stimulating. I think in general, not only FLASH, but radiation research in general is intrinsically interdisciplinary. You need biologists, chemists, physicists, engineers, and medical doctors working together. And this gives a huge I would say satisfaction to the researchers, because we don't only do research, but we learn from each other. I am a physicist, so I can teach some physics to my biologist, but vice versa, I learn a lot of biology while we work, same with medical doctors or chemists. What I expect in the next 5 years in FLASH, or even better, what I would like to occur in the next 5 years is, first of all, that we understand the basic mechanism. That's something we definitely need. We cannot use clinically something that we don't understand. So I really hope that the current progress in radiation chemistry, in modeling, and in experiments will give us more insight on the mechanism. Second, we need to prove that it's really clinically effective, so that we understand the mechanism, understand the space parameters, so that we say, okay, with these parameters, having understood the mechanism, we can really implement this in the clinics. I think this can happen in the coming 5 years, not necessarily as usual in science. I'm sure we will have surprises, But the null hypothesis, what we call the null hypothesis in statistics, is that in these 5 years we can really reach the point where we say, now we know how this works and we know what are the parameters, we can go into the clinics. And so I hope that after 5 years we will be really able to use it in clinical environments with charged particles, especially I would say maybe with very high energy electrons, but for sure with protons. And I'm very optimistic also with heavy ions. In conclusion, I want to add only one thing, especially to the young people here. FLASH and radiation research in general is beautiful, is fascinating. It's really fantastic to see how the physics of radiation has an impact on the biology, and all these can contribute to cure cancer or even other disease. It's really a fascinating field, and we need young people interested in this field, coming from all different backgrounds. If you want to work in radiation research, you have to be curious, you have to be motivated, and you have to be willing to learn every time you do an experiment. I look forward to have a lot of young people at the meeting, and I look forward to your question and to interact with you.